Hello, it is February 17th, 2016. I'm at WSSB. I'm going to do a video on the Chapter 6 review out of our geometry textbook. It's in Braille Volume 25, and it starts on page 268 straight up, or Braille page, it looks like 39, Braille page 39. And it always starts out in the review with the understanding and using the vocabulary. So we'll go through some of those words here pretty succinctly, and then we'll move on into the objectives of this chapter. So the words that you want to pay particular attention to and remember what are the definitions of and criteria for. The first word is altitude. And recall that on page 234 of this chapter, we discussed altitude, and it is the measurements of or height of your triangle. So the criteria for an altitude is it has to extend from a vertex through your triangle to the side opposite at a 90-degree angle. And it tells you the height of the triangle in that orientation. In an acute triangle, it's going to be on the inside of the triangle. In an obtuse triangle, it's going to need to be on the outside of the triangle because if it extends from that vertex perpendicular to the base, it can't go through the triangle. So the base is going to need, that side opposite is going to need to be extended to the left or the right in order to be perpendicular to it from that vertex. And on a right triangle, remember that the altitude is one of the legs, just depending on its orientation, because that's coming from a vertex at a right angle to a base. The next word is angle bisector, and that is just what it is in terms of it's an angle bisector, right? We know that bisector means to divide something in half. So an angle bisector is going to be a segment, line, or ray that's going to divide your angles exactly in half. The next word is base, and in regards to this chapter and in regards to triangles, the base can be a couple things. The base could be the side of an isosceles triangle that is not one of the congruent sides. The congruent sides are called the legs. A base can be the side that the triangle sits on. So it just varies, but it is one of the sides of a triangle. A centroid is the next word, centroid, and that's where you take your medians. So you come from each vertex of your triangle and go through your triangle to the side opposite at the midpoint, and you do that 3 times from those 3 vertexes or vertices. And where those medians intersect in the midst of your triangle, that point of intersection is the centroid. And recall with a centroid, it does something very interesting to the medians, which we figured out. It has a relationship of 2 to 1. So from the vertex to the centroid is kind of the long piece of the median, and then from the centroid to that midpoint of the median is the shorter piece. And that ratio is 2 to 1. So in other words, from vertex to centroid is 2x, and from centroid to the median is x. So all total, the median is worth 3x. So if you were told the median is 15 units, you would say 3x equals 15. You would divide by 3 on both sides, and x equals 5. So you would know that the large part, the longer segment from vertex to centroid is 10. 2 times 5, 10, and then the short part from centroid to median would be 5. And you add those together to check, and it's 15. The next word is hypotenuse. We're going to skip a couple words because they were in kind of an extra section. So the next word is hypotenuse. That's part of a right triangle. Remember that your right triangle has its own anatomy. It needs a right angle. The 2 sides that come together at a vertex to form the right angle are called the legs. And the side opposite the right angle is the hypotenuse, the longest side. And the next word is leg, so we just defined that. Median, we defined it with centroid, but we'll define it again. A median of a triangle is a segment that extends from any vertex through your triangle to the side opposite at the midpoint. So it's going to bisect the side opposite into two equal parts. And then we have two more words. Perpendicular bisector. That's going to be a line segment, a ray that goes through your triangle and at a perpendicular angle to any one of the sides, and it bisects that side into two pieces. So it could start at a vertex. It could start in the midst of the triangle somewhere and just be perpendicular to one of the sides. So you want to look for, is it perpendicular to a side, and has it split that side into two equal pieces? Then it's a perpendicular bisector. And then finally, the last vocabulary term phrase is Pythagorean Theorem. That's how we find a missing leg or a hypotenuse, some sort of missing side of a right triangle. A squared plus B squared equals C squared. Or the distance of our X leg squared plus the distance of our Y leg squared, all square rooted, and that equals the distance between the 2 points. So we're going to discuss distance formula later using the Pythagorean theorem. So those are all the main vocabulary words you want to put in your brain, refresh, review, maybe write some notes about. And then we're going to move on to covering the objectives of the different sections. So we want to move to section 6-1, which is on page 268. And I believe, let's see, it's D 268, and it should say objectives and examples at the top. It's Braille page, looks like 45. And there is a triangle on this page, pretty decent tactile. The top left vertex is P, the top right vertex is R, and that side goes through, there's a point Q. And on the right hand side, from R to the vertex V down at the bottom, it goes through a point S. And then from V back up at an angle to the left to vertex P, and it goes through a point T. From each vertex is a median. We're given that in writing above and below this problem. So from vertex P, there's a line segment extending through your triangle to the side opposite, hitting at point S. From vertex R, there is a line segment going through the triangle to the side opposite at point T. And from vertex V, there's a line segment going through the triangle to the side opposite at vertex Q. Where they intersect at the centroid point, they've labeled that to the left of it as W. So that point is W. So there's a lot going on in this drawing that we can discuss. Obviously, it's a triangle. It's a scalene triangle because all the sides are different, or appear to be different. It has three medians. We're given in writing that it says in triangle PRV, it's right below the drawing, segment PS, segment VQ, and segment RT are medians. So once you're given that, you get to go, okay, I was given that in court. I get to use that information. So then you know it's creating a centroid. You know what a median does. It comes from a vertex to the side opposite and splits it in half. That's a midpoint. So PS, S is the midpoint of the side RV on the right. So you know if you were told RV is 10 units, R to S is 5 and S to V is 5. In this case, they're telling us P, and then they're talking about the centroid also. So we know it's a 2-to-1 relationship. So if we go back to P to the centroid W is going to be 2 times what it is from W to S. So if we're told P, or the whole WS is 7.5, WS, so from centroid to the midpoint is 7.5, we know we have to double that to get PW, which would be 15. Then the whole thing together would be 15 plus the 7.5, which is 22.5. If we were told TW, so your median R to T from the top right to the midpoint T, if you're told TW, or find TW, if WR is 12. Well, you know that WR is a 2-to-1 relationship to TW. So if WR is 12, we know TW is 6. Then the whole median is 18. If you're told the side, up at the side, if you're told PQ, the top, is 14.5, what's QR? Well, that's pretty easy. 14.5, right? Because you know you were given, you can say in court, I was given that VQ is a median, therefore I know Q is the midpoint. By definition of median, I know Q is the midpoint of side PR, therefore PQ has to equal QR. If PQ is 14.5, I know QR is 14.5. So that's kind of all the work that we would be doing with medians and centroids that you might want to make some notes of. Remember your definition of a median: from a vertex to the side opposite at the midpoint, and then where they meet at the middle is the centroid. From vertex to centroid, the long piece is 2x. Centroid to midpoint is 1x. So all total, the median is worth a value of 3x. So if you're told the entire median is 21 units, 3x equals 21. 21 divided by 3 is 7. You know the little guy is 7, and the big piece is 14. All right, moving on to section 6-2. That's going to be on page 269, and it's straight up, and it's Braille page, it looks like 48, I believe. There is the objective of this particular section lesson, 6-2, is to identify and construct altitudes and perpendicular bisectors. So we already defined altitudes and perpendicular bisectors early. There's a drawing now that we can take a look at a couple of these, examples of a couple of these. There's a nice big triangle in the page. D is the bottom left vertex, C is the top vertex, and E is the bottom right vertex. From the vertex C, straight down to the base DE is a heavy line with a right angle indicator box to the right of it. And it's intersecting down at point G, they're calling that base. And then there is a line, a kind of a weird dashed feeling line with arrowheads going through our triangle to right, kind of in the midst of it, going in a vertical position with a right angle indicator at the base, and they're labeling that intersection point F. So that particular line with the arrowheads that's perpendicular to the base, that's a perpendicular bisector, because in words up above it says in triangle DCE, segment CG is an altitude and line HF is the perpendicular bisector of side DE. Now if they didn't tell you in words, you would want to know or feel tick marks between D and F and E to know for sure that that line is a perpendicular bisector. Okay? The altitude, we know it meets the definition of an altitude because it comes from a vertex to the side opposite at a perpendicular angle. So it's telling us the height of this acute triangle, acute scalene triangle. All right? So you'll need to be able to identify perpendicular bisectors and altitudes. Now sometimes they're both. So turn the page. And there is a very long lay-in on it, one of its legs. It looks like Isosceles Triangle to me. We have point R up at the top, which they've labeled it kind of top left but down a little bit. Top left vertex. Far right vertex is S, and bottom left vertex is T. From vertex S is kind of a heavy creased line going to the side opposite RT on the left. There's a right angle indicator. It's intersecting side RT at point Q. From R to Q there is a tick mark, and from Q to T there's a tick mark. So this is showing us that we have an altitude. This heavy line from S to Q is meeting the definition of an altitude, vertex to side opposite at a perpendicular angle. So if we turned our book 90 degrees to the left, it would be sitting on that base RT, and we'd be able to see how tall that triangle is, the height of that triangle. And then it also meets the definition of a perpendicular bisector because it's a line segment that goes through our triangle at a perpendicular angle to one of the sides, and it bisects that side into two equal pieces, and it's indicating that with the tick marks. So we would say that this is both an altitude and a perpendicular bisector. It also meets the definition of a median because it comes from a vertex to the side opposite at the midpoint. So the midpoint means it splits that side opposite into two equal parts. So those tick marks indicate that. So I wish they would have reminded us that it's also a median, but I am reminding you now so you know that it's all three. And if you said that on a test, that this is all three, you would definitely get some kudos from me saying, good job, you noticed that. The next page, B 269, shows a right triangle, big, long, stretched out right triangle in the middle of your page. And this is reminding you that a right triangle's altitude is one of its legs because it meets the definition. It comes from a vertex perpendicular to a side opposite. So there that top side is xy. We have x in the top left, y in the top right, z down in the bottom left. That xy is the altitude of this right triangle if it was sitting on its base xz. So sometimes your altitude is part of one of your sides of your triangle, and that happens in a right triangle. Right? I'll let you explore, the next couple drawings on your own, and you can decide whether they're a perpendicular bisector, both, or neither. The next couple drawings on C 269. It is important I'd like us to look at D 269 at this triangle to notice that this line segment coming from a vertex to the side opposite doesn't meet the definition of anything other than a line segment. So we have K as the top vertex, J as the bottom left vertex, and M as the bottom right vertex. And there is a heavy dotted line coming from vertex M to the side opposite at point Q. There is no right angle indicators. There are no tick marks of congruency or tick arcs. So all this is just a line segment splitting up our triangle into two triangles of unequal size. It's not an altitude. It doesn't meet the definition of an altitude. It comes from a vertex, but it's not perpendicular to the other side. There's no right angle indicator. It doesn't meet the definition of a perpendicular bisector. It doesn't hit the other side at a right angle and split it into two equal parts. It doesn't meet the definition of a median. It does come from the vertex, but it goes to the side opposite at just a point Q that's not the midpoint. So this is none of them. It's just a line segment in the midst of our triangle. Right? So the next section is 6-3, identify and use angle bisectors in triangles. And it starts actually on the same page we were just on, right below it. So it's D 269. And it just shows a triangle, PMN or NPM, or however you want to say it. P is up at the top right, M is down at the bottom right, and N is over at the left. There is a line segment coming from vertex M directly across to side PN at point L. And there is an angle indicator 1 at vertex M for the angle NML, and there's an angle number indicator 2 at PML. So we're noticing that angle M is getting split up into two angles, angle 1 and angle 2. They're saying in writing that in triangle PMN, ML is an angle bisector. The angle P MN is being bisected. If the measure of angle 1 is 55 degrees, find the measure of angle 2, or PML, which is 55 degrees, and then altogether the big angle would be 55 plus 55, or 110 degrees, making this an obtuse triangle, right? So you're going to use in this section angle bisector. It just means it's splitting the angle in half. So set the formula up that way. The tricky part in this section is remembering that if they're not labeled with numbers, like angle 1 and angle 2, you have to name them with the letters, like NMP, or angle NML, or angle PML. So you need to remember that when you're reading through angle bisectors. It's pretty basic to split an angle in half or add it together to get the full angle. Where the tricky part is remembering to read those letters correctly about and how you're naming your angles. So I'm not going to spend a lot of time there. We're going to move on to page G269, lesson 6-4, identifying and using properties of isosceles triangles. So on G269, did I say 264? G269, there is, and it's Braille page 55. There's a triangle up in the top half of our paper. Not too bad a one, it doesn't look like. Could be a little bigger, but we'll take it. The top vertex is A. The bottom left vertex is B. And the bottom right vertex is J. And there is a line segment extending from vertex A straight down to side BJ at point K. And there is a tick mark on side AB on the left and a tick mark on side AJ on the right. There are tick arcs at vertex A on both sides of that line segment. So angle BAK has a tick arc, and angle JAK has a tick arc, showing that those are congruent. So this is indicating to you that this is an angle bisector, that AK is an angle bisector because we have two congruency tick arcs, so showing that vertex A is being divided up equally. It's also showing you that this is an isosceles triangle because your legs, AB and AJ, are congruent with those tick marks. So we have an isosceles triangle here. In writing underneath, it says if angle BAJ, so the big angle of vertex A, if triangle BAJ, is isosceles, and AK bisects BAJ, then the following statements are true. Angle B is going to be congruent to angle J. Remember, we learned that the angles opposite our congruent sides will always be congruent in isosceles triangles. And segment AK is going to be perpendicular to side BJ because we know that it's splitting it in half, okay? And then AK bisects BJ, which is what we just said. So you get a lot of cool things going on with isosceles triangles and altitudes. It's also an altitude. It's also a median. So in an isosceles triangle, when it comes from that top vertex where the legs come together on isosceles and goes to the side opposite at a perpendicular angle, it becomes perpendicular bisector, altitude, and a median, right? So some special stuff to remember about isosceles triangles when you encounter them, all right? So you know that at that point K on both sides it's 90 degrees. That if you were told B is 40 degrees, you would know vertex J is 40 degrees. If you were told at vertex A the whole big angle BAJ is, let's say 80 degrees, you would know each side of it. BAK is 40 and JAK is 40. So be prepared to practice problems like that. There are several in the next few pages that you can practice through in regards to properties of isosceles triangles. Let's make our way to page 269. Let's see, we got I-269, and this is going to be lesson 6-5. And this is where we start using our tests of congruence for right triangles. So remember we had tests of congruence for regular triangles like side, 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 angle, side, angle, side, angle, 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 side, and no donkey, right? In in a right triangle, we can use all those tests of congruency, but we realize we always have that right angle in a right triangle. So our tests of congruency become leg-leg instead of side-side-side. Hypotenuse angle, leg angle, and hypotenuse leg. So if we have any one of those happening with our right triangles, we know the right triangles are congruent. Because really what's happening is we're experiencing side-side-side, side-angle-side, angle-side-angle, or angle-angle-side, because that 90 degrees is always going to be in the mix there as far as one triangle has 90 degree, right triangle has 90 degrees, the other right triangle has 90 degrees. So there's always going to be a 90 degree angle that's equal to the other one. So in this particular little tactile, they have two triangles. It looks like kind of in a rotated position to each other. The first one is triangle ABC up kind of towards the top right. The right angle is at vertex B. They're showing you that angle A has a tick arc and side BC on the right has a tick mark. The triangle below it is triangle DEF, or GEF, sorry, GEF. G is the bottom right, E is up at the top, or G is at the bottom left, I'm sorry. E is up at the top right and F is at the bottom right. And F has a right angle indicator, kind of tiny. G to F, it has a tick mark, and angle E has a tick arc. So we know angle A of triangle ABC is congruent to angle E of triangle EFG, and we know that FG is congruent to BC. So these are congruent because we have an angle and a leg. So these two triangles are congruent to each other by law, or LA, right? Leg angle. Because also what it is angle, angle, side, isn't it? Angle, angle, side. We have the angle A, the right angle, and then a side. Angle E, the right angle, and a side. But instead, because they're right triangles, we don't say angle, angle, side, we say leg angle. All right? So you practice those. So you want to remember that you have leg angle, you have leg leg, you have hypotenuse angle, and you have hypotenuse leg. And you're looking for any one of those to prove congruence of your right triangles. So there's some practice on the next couple pages. Remember that triangles can share legs, like on the next page. You'll kind of feel your way through a big parallelogram that has a line coming perpendicular down the midst of it, creating two triangles. And then remember that that leg coming down the midst of it, they're sharing that leg. So this looks like a leg-leg situation. Okay? Get yourself to the next page, K269, and there's a page break for 270. And that is the next section, 6-6, the Pythagorean Theorem, and its converse. This is a review section for you. You've done Pythagorean Theorem for years in pre-algebra and algebra. Good old a squared plus b squared equals c squared, right? A squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared on any right triangle. So they show that with a right triangle on the next Braille page, A270. And they're just showing you a triangle, XYZ. X is the bottom right, Y is the bottom left, Z is the top. There's a right angle indicator at Y. They're showing you from Y to Z is B, from Y to X is 16, and from Z to X is 34. And they plug all that in. They have the proof down below where they say, okay, let's write out our formula. A squared plus b squared equals c squared, Pythagorean theorem. Let's substitute in the values. So 16 for the a value, 16 squared plus b squared equals 34 squared. Use your calculators. 16 squared is 256 plus b squared equals 1156, 34 squared. We want to subtract 256 from both sides using our subtraction property of equality. We get b squared equals 900. We're not done yet. We have to square root because we want to get that little squared away from the b squared. The square root of b squared is b, Therefore, do it the same thing to the other side. The square root of 900 is 30. So that B side equals 30 units. So you practice using Pythagorean theorem to find a missing leg or hypotenuse. You also can use the Pythagorean theorem to prove whether a triangle is a right triangle or not. If you're given like three sides of 3, 5, and 4, 3, 4, and 5, 3, 4, and 5, you know 5 is the hypotenuse because it's the longest side. You go 3 squared plus 4 squared, does that equal 5 squared? Well, 3 squared is 9, plus 4 squared is 16, equals 5 squared is 29, or 25, excuse me, 25. So 9 plus 16 is 25. Yep, 25 equals 25. That would work. But what if you had 3, 4, 6? Oh, okay, 9 plus 16 is 25. 6 squared is 36. Uh-oh, 25 doesn't equal 36, so that couldn't be a right triangle. So you can use the Pythagorean theorem to prove whether three lengths of three sides of a triangle are going to be a right triangle or not. So if they're not a right triangle, they're just either obtuse or scalene. All right, finally, the next section is section 6-7. So you're going to go in a few pages. Let's see, I gotta find it here. Oh, my calculator entertaining you. Turn that off. Okay. Let's see. I think section 6-7 is down below on page C270 or Braille page 62. And let's see. I think it says find the distance, right, between 2 points on the coordinate plane. So remember, this is where we discovered on the coordinate plane, if we had any 2 points anywhere, an x and y point one place and another x and y point another place, we could find the distance between the two of them by turning it into a right triangle. And we find the distance in our x values, right, the difference in our x values. That becomes our leg, one of our legs, going back and forth. And then we find the difference or distance of our y values, right? The leg going up and down. Those become our legs. So leg squared plus leg squared has got to equal hypotenuse squared, which is the distance from the 2 points, as we learned as the crow flies, right? The quickest distance. So we use the Pythagorean theorem. Now they put it in an all fancy kind of thing where they claim they tighten it up, right? It's square root, AR, open. Then they do an open paren, x2 minus x1, close paren. They're finding the difference between the 2 points. They square it, plus y2 minus y1, difference in our y values, squared. And then the whole thing, we terminate it, and then it's square rooted. That's because they're taking you through the Pythagorean theorem, but just keeping the square root on one side, because we know in the end we still have to square root it. So that shows you what they did through that whole process on lesson 6-7, all right? And then you have some questions you need to work through where they give you some points. Like for question 31, it says points J are -8, 2, and K 0, -4. So let me get my whiteboard out and we'll kind of do this one on the whiteboard. We have our 2 points. So we have J at -8, 2, and K at 0, -4. And then if we plotted those, we would want to find the distance between those. You know, if we put a point at -8, 2, 3, 4, 5, 6, 7, 8, up to 1, 2. I'm just making a funny little graph on my board. And then 0, -4. We'd want to find the distance between those 2 points. So we have to make a right triangle and figure this out, because that's the distance between the 2 points is our hypotenuse. So one of the legs is the difference in our x values. So -8 minus 0, well, that's 8 places, isn't it? So we have 8 squared, or 64. And we're going to add that to the difference in our y values, which is 2 minus a -4, right? 2 places, and then we got to go 4 more to get to the -4. So we have 6. So we have 6 squared, and that's 36. So we add those two together, and that's 100. And then we have to square root it, because c squared is going to equal 100. We've got to square root both sides. So the square root of 100 is 10. So the distance between point J at negative 8, 2, okay, distance between point J at negative 8, comma 2, and point K at 0, negative 4 is 10 units. Because we took the difference of the x values, squared it, because that's one of our legs, took the difference in our y values, the distance, right? 2 to negative 4 is going to be a 6, a distance of 6, squared it, 36. Add those together, the two legs got to add together, so 64 plus 36 is 100. Square root it in order to get our c value, or our hypotenuse, which is 10. So the book makes it look all fancy with that huge distance formula with the square root, but really you're just remembering your Pythagorean theorem. A squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. Do the work with it, and you're going to find the distance between 2 points. Be really, really careful with your negatives. That's where students get tripped up. They, like the 2 minus a negative 4, they might not notice it would be 6, and they'd want to say maybe it's 2. All right, so that's for lesson 6-7, and that's the last section in the book. So we make our way through a couple of story problems in the review, and then chapter 6 is done. So follow along with this video, follow along in your book, and you should be able to do pretty decent review on chapter 6. All right, everyone. We'll see you in the next class.